So we're going to be dealing with integrating our natural log, or what gives us our natural log. Do you know the derivative of your natural log is 1 over u? So if you're integrating 1 over something, it should give you your natural log. So looking at this, I'm going to go ahead and pull my 2 in front. And then I have a 1 over an x with a dx by it. You should now know that when you integrate 1 over x, that goes to natural log with a plus c. Because if you're working backwards and you did the derivative of this, you get 1 over x. Now remember, whatever is after your log is positive, so that's why we have the absolute value. But because if I can take my 2 and put it up here and I'd have an x squared, I don't have to worry about x or absolute value because x squared is always positive. With the exception of 0, and it doesn't make sense that we can put in 0 because 0 wouldn't be a part of your original problem because you'd be dividing by 0. So looking over here, we have this in the bottom. I think what I'm going to do, because I'm not sure what else to do, is I'm going to just let the bottom be u. Well, if I let the bottom be u, I got to find my du to get my dx to show up. And I get this. Well, I just have a dx showing up. I don't have a 4 showing up in front of my dx. So I'm going to multiply both sides by 1/4. Huh. So if I rewrite my original problem like this, I would then get 1 over u, because the red is u. Instead of writing dx, I'm going to go 1/4 du. Well, multiplying by 1/4, I should be able to put that 1/4 in front. Then I just have 1 over u du. When you integrate 1 over u, you just get natural log with a plus c because it's an indefinite integral. Now all we have to do is replace u with what u is, the 4x minus 1. And we would get this. Now, here we're dividing by variables, sometimes using Pythagorean theorem or trig stuff to simplify it may help. Sometimes it doesn't. Sometimes when you're dividing variables by variables, u helps. When you're dealing with fractions, a lot of times it's best to let u be the bottom. So we'll let tangent be u. So if I do my du, taking the derivative, you should remember the tangent derivative is secant squared, and that's what we have here. So looking at it, we'd have a 1 over tangent times our secant squared. So tangent, once again, is u, so it's 1 over u. Secant squared dx is our du. Oh, well, it's pretty easy to integrate 1 over u. That's just our natural log with a plus c. So then we plug in what u is, which was tangent of x, with our plus c. Looking over here, we'll go ahead and we're dividing by variables. Typically, you want u to be the bottom. You also want u to be the higher of the two. They both apply here. So when you do your du, you get a 2x with a plus 2. I mean a 2x with a plus 2. We only have an x plus 1. So we don't want this 2. So we want to multiply everything by half. Now what we have here matches perfectly with what we have on top, which we could write like this, and then it would be 1 over that. Well, it would then be 1 over the red, which is our u, so 1 over u. Instead of writing the blue, that's our 1/2 du here. Multiplying by half, we could pull that half in front. Then we just have 1 over u du. Well, we've done that multiple times today. So we get 1/2 natural log of u with a plus c. And then all we have to do is take our u, which was the bottom, and plug it in for our final answer. Remembering it's an indefinite integral, that's why we need to have plus c. If it was a definite integral, then we'd have to just evaluate it and would not have to have a plus c. Now, sometimes when you have the same power top and bottom, it's going to work better to do longhand division. So you put the bottom in front of your division box, and you take what's on top, put it in your division box. Then you go x squared times what is x squared? That's a 1, so you put a 1 up here, take 1 times everything in front, and that gives us this here. Then you take the top minus the bottom, top minus the nothing is x, top minus this. This is our remainder. So this is the same thing as your quotient, which is 1, plus your remainder over your divisor. So instead of having this integral here, we could just do the integral of this. Well, that integral would be easier to do. So we could have two things added after our integral. So we could really just do the integral of the first thing plus the integral of the second thing. Well, it's real easy to integrate this. You should know that you just get x with that. This one, we might actually have to do a little bit of u substitution on. So I would probably let u be the bottom. So if we let u be the bottom, we get this. Do our du derivative of both sides, we get a du equals a 2x dx. Notice we only want a x dx, not a 2x dx, so we're going to have to do a 1/2 du. So we're still going to have this x in front because we dealt with that already. Then it would be 1 over u, and then a 1/2 du instead of your x dx from what we did over here. Well, we'll have our x plus, we could take that half, put it in front, then we just have 1 over u du. And hopefully you know by now, if you have 1 over u du, that goes to your natural log with a plus c. Well, then plug in what u is with your plus c. Now, when you're dealing with your integration and you want to know if you're right, you can always take the derivative of your answer to see if you get back to your original. If you do, that means you have the correct answer. So that's another way you can double check your work. Over here, you have variables divided by variables again. And a lot of times you're going to have to use a u on that. So you want to go ahead and take your u to be the bottom. And in this case, I'm going to let u just be what's on the inside. It may work to let u be the whole bottom, but sometimes it doesn't. If we let u be the whole bottom, we get a 2x plus 1 dx showing up, and that's not going to help us a whole lot with the top. So that's our u right there. Notice I pulled this timesing by 2 in front. So that's our u. Well, we'd have to get a du to show up. Well, if we do our derivative of this, we get du equaling a dx. Well, we had a 2x here. I mean an x. A dx, sorry. So that means that goes to du. But if we pull our 2 out, that still leaves us with an x on top. Well, all we'd have to do is take our u right here, solve it for x. So we could just subtract 1 from both sides, and that's your x. So we can come along, replace your x here in green with a u minus 1. Now, we still have variables divided by variables, but that's okay. We can take our u squared on the bottom and bring it up as a negative exponent. We could then go ahead and distribute through. Well, if we do that, we would get this minus this. That first fraction simplifies to a 1 over u. The second fraction is u to the negative 2. So really, we're just doing the integral of this first one, so integral of 1 over u du, and the integral of the next one, integral of u to the negative 2. Now this 2 is here because I distributed the 2 along with my integral through. So here we'd have 2, integral of 1 over u du, which you know is your natural log. Now here, this was 1 over u squared. 1 over u squared, all we have to do is just use the power rule, not a natural log. Natural log is what you get when you integrate 1 over u to the first. It does not work when you have a 1 over a u squared. You just use your normal power rule. So you increase your exponent by 1, So we get negative 1. Remember, this negative 1's in front to offset that exponent, and we still have to have plus c. So we now just have this. Minus minus is a plus. Well, all we have to do then is replace your u with what u was. Now u was x plus 1. And then go 2 over an x plus 1 with our plus c. Here we're asked to find y. Well, to find y, we want to go ahead and find our differential. Remember, differential is where you basically multiply both sides by dx. Now, to find y, when we have our derivative of y, all we'd have to do is integrate that. So on the left side, when we integrate our dy, we get y. That's what we want. Well, if we integrate the left side, well, you'd have to integrate the right side. Oh, wow. Now, this is really a natural log of x times a 1 over x dx. We're multiplying variables again. Well, there's a good chance that u is going to be helpful. So if we look at this, we're going to let u be the natural log because we know the derivative of natural log is 1 over x. And we get this 1 over x dx showing up. So what I boxed in here is really your du. And this is just a 1 over u. Oh, well, we've integrated 1 over u du before. We know that that's going to be the natural log of the u with a plus c. All we have to do at this point is replace your u with what u is, which is natural log of x. We get the natural log of the natural log of x with a plus c. Now, here we have the integrals of our 6 basic trig functions. Now, the top two here, this top row, you're pretty familiar with. You've dealt with that before. The bottom 2 rows you have not seen. Now, you should remember that when we did the derivative of this a lesson or 2 ago, we ended up getting this. But basically, these are the rules that allow you to be able to integrate tangent, cotangent, secant, and cosecant. So as we look here, we now need to integrate this. Find the area underneath our curve of this here. Well, we have a 1 plus tangent squared. Remember, 1 plus tangent squared is really secant squared. So it's really a secant squared inside of our square root. Well, your secant squared inside of your square root, they would undo each other, leaving you with a secant. Oh, so now we're just integrating secant. And you can see up here, when you integrate secant, we get this. Now, we don't have to worry about the plus c for our problem because we have a definite integral. If it was an indefinite integral, we go plus c. So all we're going to do is just write this here, and then just have to evaluate that. Evaluate it from pi over 4 to 0. So we take pi over 4, secant pi over 4, plus tangent pi over 4, minus what we get when we plug in 0. Well, when we plug in 0, the whole inside goes to 1. Oh, you remember that, hopefully you remember that your natural log of 1 is 0. So we really just have this in front. If you wanted to do the approximation, you could. But for your test, make sure you do your exact answer, which would be over here on the right. So suppose we wanted to find the average value of our tangent function on this interval. Well, average value goes back to the last chapter. We'd have to go 1 over and subtract our 2 bounds, the bigger one minus the smaller one, and then do our integral with our bounds of our function. So here we get 1 over pi over 4, but instead of dividing by pi over 4, you multiply by the reciprocal. And all we have to do now is integrate. Integrating tangent, well, going back to our last slide here, when you integrate tangent, you get negative natural log of cosine. So we get negative natural log of cosine, and then we have to evaluate that. So we'll leave put our negative in front with this here, and then we have to evaluate it. Remember, when you take and you plug in your pi over 4 to here, Tangent of pi or cosine of pi over 4 is this. And then you'd have to go minus what you get when you plug in this. And cosine of 0 is your 1. But remember that your natural log of 1 is 0, so we're really subtracting 0, so we really just have this right here. But that does simplify. It's really the natural log of 2 to the 1/2 minus the natural log of the 2. Because remember, two things divided after your log, you can go ahead and do log of the top minus log of the bottom. So then we can go ahead and put that 1/2 in front. Now these are like terms because they're both natural log of 2's. So inside the black here, you have a half of natural log of 2 minus 1 of the natural log of 2's, which is a negative half of the natural log of 2. So negative 1/2 natural log of 2 times that negative 4 over pi in front. Negative times a negative is positive. The 4 over the 2, you should know it's going to simplify, and we get 2 over pi natural log of 2. And here's the approximation of that also.